Welcome. Today, we're digging into a real classic, a problem from a textbook that has been a rite of passage for physics students for decades, i.e. Irodov's Problems in General Physics. We're going to take on problem 1.35 and just solve it together, step by step.
So here's our game plan. First, we'll unpack what the problem is even asking. Then we'll jump into the calculus to map out the particle's actual path. After that, we'll figure out its acceleration, which you'll see is the key to how that path bends. And finally, we'll put it all together to see the big picture physics principles in action.
All right, let's dive right in. Before we can start solving anything, we've got to get a really solid grasp on the setup and what we're actually being asked to find.
Okay, so what are we looking at here? The problem hands us a velocity for a particle. Now the x direction part, the AI bit, that's just a constant. Simple enough, but check out the y direction, bxj. This is the key. The upward velocity isn't fixed. It actually depends on the particle's x position. So the farther it travels horizontally, the faster it moves vertically. That relationship is the whole puzzle we need to solve.
So, boiling it all down, our job is to turn this velocity information into a geometric picture. First, we need to find the actual shape of the path. That's y of x. Then we need to figure out just how sharply that path is bending at any given point, and that's the radius of curvature, r of x. All right, let's get into part A, finding the trajectory. The goal here is to come up with one single equation that describes the shape of the path, connecting y directly to x without having to worry about what time it is. And to get there, we're going to follow a classic, super reliable three-step playbook from kinematics. We'll break the velocity down, integrate to see how position changes over time, and then mash those two equations together to get rid of time completely. So let's start with the easy part, the x direction. Our velocity vector tells us that vx is just the constant a. Now, since velocity is just the rate of change of position, we can write dx dt equals a. To get back to position x, we do the opposite. We integrate. The integral of a constant a is just at. And since the problem says we start at the origin, our constant of integration is 0. Boom, x equals at. Now for the y direction, and this is where it gets interesting. We know that vy is bx, but wait, we just figured out that x is at, so we can substitute that right in. This means our y velocity is actually bat. It's changing with time. So to find the y position, we integrate that expression with respect to time. The integral of bat gives us y equals 1/2 bat squared. And now for the final magic trick. We just need to merge our two position equations. From our x equation, it's super easy to see that time t is just x over a. So we take this expression for t and plug it straight into our y equation. A little bit of algebra, and what do we get? Y equals b over 2a times x squared. And hey, look at that. That's the textbook equation for a parabola. It makes perfect sense, too. The particle is just cruising along at a constant speed horizontally while it accelerates vertically. Okay, so we've got the shape of the path. That's huge. But before we can dive into part B and figure out the curvature, there's one more piece we absolutely need, the particle's acceleration. So how do we find acceleration? We take the derivative of velocity with respect to time. Now, this is a really important point. You have to use the version of velocity that depends on time, not position. So we use v equals ai plus btj. The derivative of the ai part is 0 because it's a constant. The derivative of btj with respect to time is just abj. And there you have it. The acceleration is a constant vector pointing straight up in the y direction. Awesome. We have the acceleration now, which means we are fully locked and loaded to tackle the second part of the problem, finding the radius of curvature of our parabolic path. So what even is the radius of curvature? Well, imagine you're at some point on the curve and you try to draw a circle that perfectly kisses the curve right at that spot. The radius of that circle is the radius of curvature. It's really just a measure of how bendy the path is. A tiny r means a super sharp turn, and a giant R means the path is almost a straight line. The formula we're going to use is r equals v squared over wn, where v is the speed and wn is the normal component of acceleration. You see, acceleration really has two jobs. The tangential part points along the path, and its job is to speed the particle up or slow it down. But the normal component, wn, points perpendicular to the path, and its only job is to change the particle's direction, to make it turn. And since curvature is all about turning, wn is the part we care about. Okay, let's start building our formula. R equals v squared over wn. First, the numerator, v squared. That's just the speed squared. Speed's the magnitude of our velocity vector. V equals ai plus bxj. So, using the Pythagorean theorem, the magnitude squared is just the sum of the squares of the components. That gives us v squared equals a squared plus bx squared. Easy enough? All right, now for the trickiest bit of the whole problem, the denominator, Wn. Remember, this is the piece of the total acceleration that's perpendicular to the velocity. Our total acceleration w points straight up, but our velocity v is pointing along the curve. We need to find the component of w that's pushing at a right angle to v, forcing it to turn. A little vector math shows that the magnitude of this normal component works out to a squared times b divided by the speed. So now we've got both parts. Let's plug them into our main formula. R equals v squared divided by Wn. We've got our v squared expression on top and that expression for Wn on the bottom. I know it looks like a bit of a monster, but trust me, with a little algebra, it's going to clean up really nicely. And after all that, here it is, our final answer, the radius of curvature r as a function of x. You can even see from this that right at the start, when x is 0, the radius is at its smallest, a over b. That's where the curve is sharpest. Then, as the particle moves out, x gets bigger and the path gets straighter, so the radius of curvature gets larger and larger. So let's just take a step back for a second. We solved it, which is great. But what's the big picture? What are the really fundamental ideas about motion that this one problem from Irodov managed to teach us? Well, first, it hammered home that to get from velocity to position, you integrate. Second, it showed us that classic trick for finding a path. Find x of t and y of t, and then just get rid of t. And finally, and maybe most importantly, it gave us a real-world reason to care about normal acceleration. It showed us that the part of acceleration that's perpendicular to the motion is what actually defines the geometry, the bendiness of the path. And to wrap up, I'll leave you with a little something to think about. Our velocity was v equals ai plus bxj. What would happen if that constant b was negative instead? What would the path look like? How would the physics change? Let that one simmer a bit. Thanks for working through this with me, and I'll catch you on the next one.